Students, now let us discuss about retention of configuration during the chemical reaction. See, you consider this X okay. This what we are representing one molecule in like general molecule in 3 dimension. Now, this involves reaction. Here Y displaces X and gives rise to product. You can note here that in what direction X was there here, the same direction is Y is there. The configuration of the molecule is not changed, it's not changed. Or we can say that during this reaction, preservation of integrity of spatial arrangement around the asymmetric carbon atom is retained. Spatial arrangement around the asymmetric carbon atom, it retained as it is. So, in a reaction in which the preservation of integrity of spatial arrangement of different groups around the asymmetric carbon atom retains, in that reaction we say that retention of configuration has taken place. In that, configuration will retain as it is. In which case it happens? When it possible, we will take one with the example. You take the example of 2-methyl butan 1-ol. It will be CH3, CH2, CH3 and CH2OH. Second position methyl group is there. So, 2-methyl butan 1-ol. Let me write the configuration with respect to this carbon, okay, because look at this carbon, one ethyl group and here CH2OH group and H group. So, this carbon is chiral carbon atom, asymmetric carbon atom, because 4 different groups are attached. So, with respect to that carbon, let us write the configuration C CH2OH right H and here CH3, here CH2, CH3. So, you can see CH2OH group and here H, here I have written CH3 group is away from the observer CH3 and this CH2, CH3 here. Now, if is reacted with HCl, this OH is replaced by Cl, then you get the product. CH2OH, sorry, CH2, Cl and here H, this CH3 remains as it is, the CH2, CH3 also remains as it is. Imagine here we have taken minus 2-methyl butan 1-ol. That means it shows it rotates the plane polarized light towards left anticlockwise direction. And during the reaction, this carbon oxygen bond is broken. But look at the bonds of the asymmetric carbon atom. This is asymmetric carbon atom. During the process, all the bonds of the asymmetric carbon remain as it is. It is the bonds of the asymmetric carbon atom are not involving in the reaction. no bond of the asymmetric carbon atom is broken during this process. Therefore, what configuration this asymmetric carbon has in the reactant, same configuration will be remain in the product, and because of that reason this product is, you can say it as 2-methyl, not 2-methyl, you can here chlorine is there. So, 1-chloro 2-methyl butane is the name, and it will have exactly similar optical activity. Means here you have seen that this minus 2-methyl butane 1-ol, and that means it rotates the plane polarized light to the left or anticlockwise direction, and the product also rotate the plane polarized light towards the left anticlockwise direction, because configuration is retained as configuration of the asymmetric carbon atom retained as it is. Therefore, optical activity will be in the same direction. The magnitude may not be same. Imagine if this shows one 12-degree specific rotation, it will not show exactly 12-degree of specific rotation, it will be different, but it will be on the same direction. Okay. And that is the importance of retention of configuration. Next, we will go for retention, inversion and racemisation. See, consider one compound, let us write it like this. X CH2 CH3 H CH3. You can see that this is asymmetric carbon atom, because CH3 group here, H group here, CH2 CH3 and X, all 4 groups are different. So, this carbon atom is asymmetric carbon atom or chiral carbon atom, and that is undergoing reaction. Here X is replaced by with one Y. You get the product. If you get the product like this, CH2 CH3 Y and H CH3 Y. This is considered A. Look at this, what configuration this reactant has, the same configuration is present here. So, if you get only this molecule as a product, then you say retention, 100% retention of configuration. Now, you think if other way, when Y is replacing X, you get configuration like this. H2 CH3 and this is CH3 H, and here you get Y. We compare this configuration with this, it got inversion of configuration has taken place. So, if you get only B as product, inversion takes place. Now, in a process, you get A and B, both A and B to equal extent, 50-50%. What happens? That time racemic mixture you get. racemic mixture you get. You can understand this by considering you take this as a D isomer. This reactant is D isomer. Imagine this is D isomer. That means it rotates the plane polarized light to the clockwise direction, and it has optical rotation, let us say 17 specific optical rotation plus 17 degree. What about now optical activity of this? Here configuration is retained, therefore, this will show same optical activity in same direction, and it will have, let us say something 19 degree plus, and this will be D isomer. See, specific rotation will not be retained because this compound is different with respect to this, okay. But what is retained is the direction in which optical rotation takes place. What about here? Here configuration gets inverted, therefore, this will be L isomer, and it shows minus 19 degree specific rotation, minus 19 degree specific rotation, because only you got only B and their inversion of configuration takes place. Now, here when you get 50% of A and 50% of B, here A rotates the plane polarized light towards the clockwise direction, and specific rotation is plus 19 degree, and this B rotates to the clockwise anti-clockwise direction minus 19 degree. Equal optical magnitude of optical rotation is exactly equal, but only the direction is different, and this mixture contains equimolar quantity of D and L isomer, D and L isomer of the same compound, and that is racemic mixture. Therefore, this process is known as racemization. So, from this you can understand that when retention of configuration takes place, you get a product which has optical activity in the same direction with respect to the reactant. If only inversion takes place, then if you take D isomer as a reactant, you get product which is L isomer. If you have taken L isomer as a reactant, you get D isomer as a product. But in the process you get 50% in the process 50% retention of configuration takes place and 50% inversion of configuration takes place. That time you get racemic mixture, therefore, that process is known as racemization. Last one. Students, after learning basic principles of stereochemistry, now we are in a better place to discuss stereochemical aspects of SN2 and SN1 mechanism. First, let us consider SN2 mechanism. What happens in the case of SN2 mechanism? So, you take one example of 2-bromo-octane. Then what is this 2-bromo-octane? You can write the formula as CH3 CH2 5 times CBrH CH3 1 2 here 5, so 7 and 8 octane 1 2 second position bromine, so 2-bromo-octane. And note here this carbon. To this carbon bromine is attached, methyl group is attached, hydrogen atom is attached, and this group we will write it like this now C6H13, this C here 5, so 6C and total 13 hydrogen, then carbon, bromine and hydrogen atom CH3. So, you can by this carbon attached to 4 different groups, therefore chiral carbon. So therefore this molecule possesses one chiral carbon atom, and that molecule becomes asymmetric or chiral, and therefore that is optically active. So we have taken an optically active alkyl halide. When it undergoes SN2 reaction, what happens? We will write 3-dimensional configuration with respect to this carbon. So carbon, bromine, then we will write H here, and that is that C6H13. So we will write this side C6H13 and CH3 group here. Now this undergoes nucleophilic substitution with the base of OH minus, and when reaction takes place according to SN2 mechanism, you know that nucleophile approach the carbon atom from the back side. So it won't approach along the carbon bromine bond, it approach opposite side. So you get the product, it will be C and OH H C6H13 CH3. So what happened? Inversion of configuration takes place. Therefore, if this molecule we have taken as a minus or L form, L isomer, or minus, what is that, 2-bromo octane, the product what you get will have L isomer, therefore plus you can say octane 2-ol. See here inversion of configuration takes place during SN2 mechanism. Complete inversion of configuration takes place. Because of that reason, if you take L isomer as a reactant, you get D isomer as a product, and if you take a D isomer as a reactant, then you get L isomer as a product during SN2 mechanism, because during SN2 mechanism inversion of configuration takes place. Then we will go for SN1 mechanism. What happens during the SN1 mechanism? Take SN1. We will understand the example of 2-bromo butane. It will be CH3 CH2 CH Br CH3. You can note here this carbon is asymmetric carbon, bromine group, here CH3, here H, and CH2 CH3. All the 4 groups are different. So again this molecule possesses chiral carbon atom, and the molecule is asymmetric, and it shows optical activity. And this optically active compound, when undergoes reaction, particularly SN1 reaction, what happens? Let us write a 3-dimensional configuration with respect to this carbon. So carbon, bromine, here H, I will write CH2 CH3, and CH3 is away from the observer. Now if this undergoes nucleophilic substitute reaction, when this molecule undergoes nucleophilic substitution reaction according to SN1 mechanism, you know that in the first step formation of carbocation takes place, and that carbocation will be like this, H CH2 CH3 and CH3 here, and with positive charge here, plus Br minus. And you know that this carbocation is has planar geometry, because this here this carbon is sp2 hybridized. Because of that reason, this carbon has planar geometry. In the second step, nucleophile attack on this carbocation. So let me write this new carbocation here, H CH2 CH3 CH3 plus. Let us take here. Now imagine nucleophile attack from this side. What you have to consider is in the reactant, in the same side bromine atom was there. So here nucleophile also attack from the same direction. As this molecule carbocation is planar, you know that there is an equal chance of attacking from this side and opposite side also. So if it attacks, nucleophile attacks the same direction in which bromine atom was there, you get the product like this, H CH3, this is CH2 CH3, and you get OH. If you compare with the reactant, here it looks like retention of configuration takes place. Therefore, if you have taken, this is, let us say, D isomer, you have taken D isomer, okay, means it rotates the plane polarized right to the clockwise direction, and this product also will be D isomer. Now there is a other 50% chance that nucleophile attack from the opposite direction compared to the bromine atom was, okay, in the direction which bromine atom was there in the reactant molecule, opposite to that nucleophile attacks. So that time what will be the product? So OH and H here, CH2 CH3, this is CH3. If you compare this configuration with the reactant, inversion of configuration takes place, and this will be L isomer. This will be L isomer. So you get 50% product which is D isomer and 50% product which is L isomer. So during the SN1 mechanism, 50% retention of configuration takes place, 50% of inversion of configuration takes place. Because of that reason, you get equal proportions of D isomer and L isomer as a product. Therefore, what will be that mixture you get during the reaction when the reaction takes place according to SN1 mechanism, and that will be racemic mixture, because you got equal proportions of D and L isomer as a product, and that will be a racemic mixture. Therefore, SN1 reaction, you can call it as a racemization. So at the end, what you can understand is, during the SN2 mechanism, inversion of configuration takes place. So if optically active alkyl halide take part SN2 reaction, then you get product which has optical activity opposite that of the reactant. But if you take if the optically active alkyl halide compound undergoes SN1 mechanism, the product will be racemic mixture.